So with no further ado, Artemi Novoselov is going to talk about deep learning with uncertainties for onset time prediction.
All right, let's go. Wonderful. You can see the presentation, you can see me. So I'm going to be speaking a bit about myself, about phase picking, about regression versus classification tasks, and about uncertainties, confidence, and some results. So let's start with me. I had a very exciting life. I started in Russia, in Moscow State University. Then I moved to Norway in the Regional University of Science and Technology, where I received a Master of Science in Geoscience and Geophysics. And then I moved to Austria for a PhD studies in Geophysics x AI.
Artemi, there's no prize for the most words delivered in 15 minutes.
Then I moved to Israel, and now I'm here in the Bay Area. I do mountaineering techniques, running, hockey making concerts, and going to beaches. But enough about me. Let's talk about science. So today we're going to be talking about phase picking. Let's say we have a waveform, a seismic waveform recorded with a seismometer. You would see that there are distinct features on this seismic waveform, and you would think, oh yeah, this is wonderful, let's peak those waveforms. So the conventional way to do that is to deploy a technique called STA-LT. Just a short reminder how it's done. You would have a short time average window, you would have a long time average window, you would roll those windows through the waveform, and you would plot the ratio between the short time period average and the long time term average. As soon as this thing exceeds certain threshold, the picker would trigger, and you'd say, oh yeah, this is the peak I'm trying to make. This is the phase I'm trying to pick. Wonderful. So using this method, you would get the P peak and the S peak, like a primary wave and secondary wave peaks, and it's marvelous, isn't it? If you were to associate those peaks and then project them, you would have a map where all of these earthquakes would be originating from. And it would look something like this. The big problem with this approach is that first, it has massive false triggering rate in the presence of noise. And second, it's not really sensitive to phases buried in the noise. Let's say it would never pick this particular arrival here or anything like this. So then the community, the seismological community thought, okay, could we use something better? And they came up with like a number of nicer methods how to do that. And one of the latest methods how to do that is deep learning. People said, okay, how about we deploy the task of phase picking to deep learning model? We would have some deep learning thing that would predict where the peaks should be. And the way people are doing that, at least the way PhaseNet is doing that, they would try to assign some probability to each sample. We're going to talk a bit more about this in the future. Using this technique, you would have way more earthquakes detected. You would have a better illumination of tectonic features, faults, and whatnot. Right? This is the map produced with the PhaseNet, a notorious phase picker developed in this lab here. What the PhaseNet is doing is essentially it would divide the whole waveform in an array of samples, and then for each sample, it would try to predict, is this sample a P peak or not a P peak, or like an S peak, doesn't it? So for the first cell here, it would be like, not really. For the second one, it would be like, oh, maybe it is. For the third one, it would be like, yeah, this is definitely the P peak, and so on and so forth. You got it. So essentially, it boils down to classifying each sample as, does it contain the peak, or doesn't it contain the peak? So this is the traditional approach used up to now. The approach I'm suggesting is slightly different. How about instead of classifying the array of samples, we would just regress to a single number. We would run the whole waveform through the neural network, and then the neural network would output you a single value, just like time. Let's say this thing would output you like which sample corresponds the best to the P peak, and let's say we have ground truth that the P should be 3.21 seconds, and we'll predict 3.2 seconds, which is great. The best theoretical maximum of prediction in this kind of model is sample accuracy. Like you cannot predict better than the number of samples you have. In the regression setting, you can output the predicted value, and theoretically, you can have a subsample accuracy. which is mostly limited by the ground truth you have. Like if analysts are able to produce a subsample accuracy, you are able to produce it as well with deep learning. So the way it works, the way my neural network works, is as follows. You have the input waveform, which is 3-component. You would run it through a feature extraction model, and it will represent the data sequentially as some internal representation. You would argue that it's probably sensitive to the amplitudes, relative, and so on and so forth. A typical block of this thing would be like this. You would have some layers, some convolutional layers, some activation function, some pooling layer, and some normalization layer. And all of these blocks would be like that. Then you would run this final extracted feature through a regression model, which is a linear layer. Just a normal regular perceptron. So you would have, in this particular case, you would have a linear layer that maps an input of 1024 by 2 to a single number as here 0.5. If you wanted to, you can map it to 2 numbers. You can predict p peak and s peak. If you wanted to, you can predict as many numbers as you want to. You can have as many phases as you wanted to. You can predict some other values like the polarity of the peak if you needed to, and magnitude, or whatever else you can come up with. Just to compare with the notorious PhaseNet, so the PhaseNet works like this. You would have the same input, which is a 3-component waveform. You would run it through the PhaseNet, and it will output you a pseudo probabilities of the peak. Then you would have to threshold those probabilities, and then take the mean, and this is your P and S peak predictions. So this is a result of running my neural network on the sample from EKC dataset. As you can see, the neural network predicts the P peak arrival and S peak arrival pretty accurately. If you will do the same on a larger number of samples, you would see the distribution of residuals in red for P peaks and S for S peaks in seconds. This is pretty reasonable, right? So if you were comparing to other methods, you would find that in the current form, my neural network is performing better than Bart Credible for basic phase AI DPP. And it's performing slightly worse than PhaseNet and Nuclear Transformer and GDP for the regional setting. For the teleseismic events, it's performing better than any other method, including PhaseNet, except for the EQ Transformer. For the S peaks, we're performing almost the same as the EQ Transformer. As you see, the residual here is 0.15 and mine is 0.16. Wonderful. So let's talk about the pseudo probabilities. As I mentioned before, right, those probabilities arise from basically a certainty of each sample being the P peak. But those are not the real probabilities. They can become true probabilities if you calibrate it right, but out of the box, they are not the true probabilities. They have nothing to do with reality. Which brings us to the following question: how could you actually express the probability of the peak? One way to do that is to think about probabilities as uncertainties. There are 2 types of uncertainties. There are aleatoric uncertainty and there is epistemic uncertainty. Combined together, one is the uncertainty of the data and the other one is uncertainty of the model. Combined together, you get a predictive uncertainty. Predictive uncertainty can also be interpreted as model confidence. Basically, how confident your model is in the prediction that it's making. All neural nets are wrong, but neural nets that know that they are wrong are useful. So the way to do that would be there are 2 conventional methods to do uncertainty estimation in the deep learning. One would be a Monte Carlo dropout. When you train a neural network, you kill some of the neurons, you run the inputs through these killed neurons, and you get some output. And then in the test time, you would kill again different neurons. Let's say this one here in the one realization, and the second realization, you kill those 2 neurons, and so on and so forth. Then you make those predictions, you average those, and you compute the variance of the predictions. The other way to do that is to deploy batch sampling. When you have exactly the same models, but you train them with different random seeds, so they're given slightly different predictions. So you have that, you average across those, and you get the result. There are some caveats that we're not going to discuss with this. But there is a way to combine the power of 2 with the idea that is called mask sample. The way it works as follows: you have the input, you make a copy of this input at the test time. You run this input through the neural network, through the single neural network, and those inputs would go through different subnetworks. Each of these subnetworks would predict to you a value. Then you can gather all of those values, get the mean and the variance of each prediction. And you can interpret it as the confidence of the peak. Basically, the more subnetworks are agreeing with each other, the higher the confidence. If the subnetworks are disagreeing with each other, the confidence is lower. So this is what you get, right? You run the same sample through the neural network, and you actually get the confidence of those predictions. This is the distribution, just very tight. So you could test what's happening if you take the sample, you introduce some noise to the sample, and you keep introducing this noise, and you see how the confidence is dropping. So the more noise you see, the less confident your model is in this prediction. This has some interesting implication. Let's say you have a seismic network, you run your data from the seismic network through the phase peaking mechanism, the algorithm, and it produces you phase peaks at different station indexes, right? This is the map you would have. Then the next task would be to associate those predictions with some particular earthquakes. Should you have the narrow network that outputs the confidence, you can actually filter your predictions on the confidence, which makes the phase association task so much easier. Because as you filter it out, right, you essentially left out with very confident peaks, which is great. And as a bonus, the neural network I produced doesn't have any shift variance. One of the problems that Yongsoo Park identified with FaceNet was that if you shift the prediction slightly, the result of the prediction is very different. It originates from a bug in one of the layers in the, one of the conventional layers in the neural network, which is the convolution. So basically, if you do it as people used to do that, you introduce some aliasing into the model. You can fix it. It's a drop-in replacement. You can if you guys have any neural network models, you can replace it in your code. You would just have to retrain the model, and then your model is not going to have any shift variance. For a reference, read the paper, make convolution shift invariant again. And just to give you conclusions, one can safely replace counterintuitive classification scheme with a very intuitive regression scheme for phase peaking. This allows to predict as many parameters as you wanted to. In general, regression is very underexplored in deep learning research. You would say, well, people don't do that. Like, why would I do that? And apparently the answer to that is that people don't do that because they didn't try to do that. For industrial applications, it's just so much, like you just don't really need to predict any continuous variables. It's more of science kind of thing, or like a higher level industry, not the consumer tech, which deep learning is mainly focusing on nowadays. One can also use the uncertainty measures to quantify confidence of the phase peaker, which has some nice implications. Uncertainty is another unexplored area of deep learning research. There are a number of labs that are working with uncertainties right now, and one of the most notorious ones is Google Brain. They're making some steady progress, but still, like there's so much room for scientists to explore the uncertainties in deep learning. And as a final note, it is also possible to update the deep learning architectures in a way that doesn't introduce shift variance into the neural networks. Thank you very much.
Thank you. You beat your previous record time by 2 minutes. Questions, please. Yes.
It seems like EQ transformer had pretty good results, as you showed. Have you thought about trying to combine these two, where you do like a transformer architecture with this regression tacked on at the end?
Before you answer that, could you please explain what EQ transformer is?
So EQ transform is another very notorious neural network developed in this lab here. It does perform a great job, and the problem with the EQ transformer that is very heavy. Like it has lots of parameters, it's very, very dense, right? So I thought it would be nice to try to do something lighter that would perform the same function, but it would take like half of the training time, like that you can actually run on the CPU in like instant, sort of a real-time kind of model. So the EQ transformer was a bit too heavy for that. So I thought, how about I just try to strip everything from the EQ transformer and just develop like an optimized version of it that doesn't use any transformer. Because they're too heavy to use. So yeah, I mean, essentially our neural networks are pretty similar. I just don't have like a bunch of transporter layers in the end, but like the encoder part is very similar. It's just hyper optimized towards the PTP or things speaking in general.
Gotcha. Thank you.
My question would be, you mentioned the variance in shift, different time, the confidence is different. Do you think it's caused not by the architecture, but by the training data set? In the training data set, they are not evenly distributed.
Well, it's mostly goes by the way convolutions work. Because when you try to do convolution and then pooling, you are introducing aliasing into your results. Like every time, like you slightly shift, and you actually get a different feature. Like the way you convolve your signal with your filters is just different. But it doesn't have to be this way. Like it's a easy drop-in replacement that you can do. People do it now. After 2019, it should gain some popularity. It doesn't really have much to do with the data set itself.
While we wait for the next question, I'm going to invite the next speaker to come up and get the computer ready.